Hello students, good morning. Okay. Hello, good morning students.
Good morning, ma'am.
You are
Morning,
able to
ma'am.
hear my voice now. Very good, very good. Very good, Prasanna and others. Good. Okay, let us start our class. Time is sharp 11:30. Let's proceed with our regular discussions. Yesterday, have we discussed about instrumentation amplifier ma for section C? Have we discussed?
No, ma'am.
No? Okay, okay, right. Okay, then I'll discuss that also. After that, we'll discuss sample and hold circuit. Okay. Let us see what all we have discussed in previous class. Of course, in the same class, I have recollected and recapitulated, but still, voltage to current converter we have seen. There are two types of voltage to current converters, floating type and grounded floating load and a grounded load. Okay, and then the circuit diagram, and here just we have written KCL. Of course, IB is 0, so IL will be equal to the current that is flowing. This IL is same as this current, and finally we have written what is the voltage drop across resistor. From that IL, which is equal to VI by R1, we have seen. Similarly, voltage to current converter with grounded load, and this grounded load, here also we have applied KCL, right? This we have named it as R, and at this node we have applied KCL. Current I1 plus I2 is equal to IL, and I1, I2 respective values we have written. Okay, and after rearranging that, and we also have written what is the expression for what is that uh, gain of the amplifier when it is converted in non-inverting mode, right? So that is the closed loop gain of the amplifier, ACL we say, right? ACL, closed loop gain of the amplifier when it is connected in non-inverting mode. We know it is 1 plus RF by R. RF and R all are same, therefore we get that gain is equal to 2, and gain is nothing but V naught by V in. So V naught by V in is equal to 2, so V naught is equal to 2 times V in or 2 times VI. Okay, so one more announcement I want to give you, I forgot. That is today we have some supply fluctuations. Okay, because of that, sometimes when there is no power, I may be disconnected, right? But still my class will be there, you will be in the classroom. Just it is like in the physical classroom, when all of you are sitting, I will be teaching, but suddenly I came out of your class, right? Again I will come back to your class. Okay, like that here also in online class, in this channel you will be there, and if at all if I have problem, how, if you have problem, how you are leaving the class and again you are joining. Similarly, if I have network issue, I will come out of that class, again I will come back to that class. Okay, so you don't worry about your attendance. Today somehow from supply itself we have some supply fluctuations. During I mean morning we had that fluctuations from 10 to 10:30. Later it's okay, now there is no problem. If at all, if such problem arise, don't worry about your attendance. I can take your attendance when I join the class, right? Because I am not ending meeting, just I am leaving in between and again I will join. Therefore all your record will be there, so don't worry about your attendance. Okay, because morning it happened like that, so people were worried about attendance. If at all, if you have such doubts, you can give your register number in your chat box, but you need not doubt that. Okay, so now IL we have expressed, and after that the applications of voltage to current converter we have seen. Then current to voltage converter, just current source and one resistor here, that's all. And this is having so many applications, like where we want current to voltage conversion. So like photodiodes, as an example, photodiodes. And these photodiodes, when we have when light falls on this photodiode, it will produce some current proportional to the light, amount of light falls on it. So therefore, like that, from such source we will get current here, and that current should be divided into two branches, but here it is 0 because of the high input impedance here, and therefore this same current Is is coming here. Now when you write V0, V0 is nothing but minus Is Rf, and therefore you can say that output voltage varies with respect to input current. That means if there is any variation, because if the light is more output current will be there, V0 will be high. If the light falls on this photodiode is less, then current will be less, output will be less. So from this we understand that what is the amount of output voltage you want, all that. Okay. So like that, photovoltaic cells, photocells, photodiodes, all these they produce output current. Such applications we use where we want to measure what is the voltage output from that diode. All that if you want to measure, you can use this current to voltage converter. Why we call it as current to voltage converter? Output voltage is expressed in terms of input current. Okay, if there is any variation in input current, there will be corresponding variation in output voltage. So thus we can design a current to voltage converter. So V2I, I2V we have studied, then integrator we have studied in a detailed manner yesterday, right? That is OpAmp and R and C values, right? Here we have written Kirchhoff's current law, right? This IB is equal to 0 because of the high input impedance here. IB is 0, and then I1 is equal to IF. So what is I1? What is IF? Those two we have written. So I1 is equal to IF, and IF is current through the resistor, capacitor there. So capacitor current and voltage relationship is this: IC is equal to C dVc by dt. So here C is Cf, d by dt. V is nothing but V2 minus V0. So it is this is V2 minus V0, this voltage. So those two we have written here, and after rearranging this equation, we got V0 is equal to integral of V in. So we can say that this is the circuit which acts as integrator. Okay. After that, when you give a square wave, integrated output voltage we get. When you give sinusoidal wave, this is the integrator output. Okay. Then this is the frequency response, F equal to 1 by 2 pi RC. And then the differentiator we have seen, R and C values exchanged. And when you exchange, again same KCL we write here. Here it is 0. So IC is equal to IF. What is IC? What is IF? IC, IF. What is IC? What is IF? And when you rearrange this equation, you will get V0 is equal to some derivative of V in with some constant. Therefore, we say that it acts as a differentiator. This is the frequency response. And when you give sinusoidal wave, differentiated sinusoidal wave, that is cosine wave we will get. When you give square wave, you will get a spike. Like that, you can obtain these waveforms. So when you come back to the college, you will be having LICA lab, and what all you are learning now, you are going to listen again in your lab, and you are going to see with your own eyes in your CRO by designing these circuits. So practical circuits you are going to design, right? I think yesterday we have covered only up to that for C section. C section only, right? For A section I have added this also yesterday, right? Let us see what is an instrumentation amplifier, right? What is an instrumentation amplifier means, first let us see to understand what is an instrumentation amplifier, what is the role of this instrumentation amplifier, we have to understand an instrumentation system, right? This instrumentation system, it has some input stage and output stage, and in between it has intermediate stage, right? So any instrumentation system has these three stages: input stage, output stage, and intermediate stage. Input stage is mainly a transducer. That means there will be a transducer which can convert some physical quantity into an electrical quantity, right? Always transducer, we know it is a transducer is a device which converts one form of energy into other form. In real life, we know what is that? If you want to measure temperature, temperature sensor will be there, and it will convert the temperature into equivalent electrical signal. Humidity, like that, whatever physical quantities, physical parameters that you want to measure in the real life, that can be converted into electrical signal by using a transducer, right? After measuring that quantity in electrical form, that should be connected to the output stage actually, right? So this output stage consists of some displays, some indicators, some magnetic recorders, like that. Okay. Now the output of this transducer sometimes will not be able to drive the devices that are there at the output. The output of the transducer is not sufficient to drive the output indicators that are used at the output stage. Therefore, what we do is the output of the transducer is connected to an instrumentation amplifier. This instrumentation amplifier will strengthen that signal, and then it will be connected to the output stage, right? So that is the importance of the instrumentation amplifier, right? So this instrumentation amplifier main role is to amplify the output of the output coming from the transducer, right? So because the output of the transducer cannot drive the indicator or display devices, therefore some amplification is required. Such cases we go for this instrumentation amplifier. Okay, so the signal source of instrumentation amplifier is the output of the transducer, right? So what is the signal to the instrumentation amplifier? It is the output of the transducer. What is the major function of the instrumentation amplifier? To amplify the low level output signal, right? So to amplify the low level output signal of the transducer so that it can drive the indicator or display, right? So so that it can drive the indicator or display. That is the major function of any transducer, right? There are different transducers, different instrumentation amplifiers available, right? Instrumentation amplifier ICs are available, and sometimes actually these are used in industrial applications, right? So the requirements are rigid, right? There are rigid requirements for instrumentation amplifier, right? If the requirements are not that much rigid, if the requirements are not that much rigid, then we can use our general purpose OpAmp as an amplifier, right? So but there are some, if it is not too strict, we can use our OpAmp. Otherwise you can use direct instrumentation amplifier IC. So what are the various instrumentation amplifier ICs? MUA725, ICL 7605, LH0036, like that. There are some, these are called special purpose op-amps, right? These are called special purpose op-amps, and we say here these are, if the requirements are not rigid, we can use this general purpose op-amp. Otherwise you can use directly the instrumentation amplifier ICs. That is what about instrumentation amplifier. In today's class, okay, after that let us also discuss about the sample and hold circuit. Okay, today's class what all we are going to study is first instrumentation amplifier over, and then what is that, sample and hold circuit. After that sample and hold circuit, after that comparators we are going to study. Again in comparators we have inverting comparator, non-inverting comparator, and inverting comparator. So all these I aim to complete. After that, if time permits, we also see regenerative comparator, which is nothing but a Smith trigger, right? Regenerative comparator which is nothing but a Smith trigger. So if we study up to Smith trigger, we will study all comparators, and before that let us also study sample and hold circuit. You know that we are studying linear and non-linear applications of OpAmp, right? When we say linear and non-linear applications of OpAmp, each class we are studying so many applications. Before this, we have studied V to I converter, I to V converter, and then what is that? And before that, we have studied buffer amplifier and inverting summing amplifier, non-inverting summing amplifier. Like that, so many applications we have seen. And in today's class, we also have seen instrumentation amplifier. And we are going to see some more circuits like sample and hold circuit. This is another application of OpAmp. And after that, some comparators. How do we design comparators using OpAmp? That means using OpAmp, you can design differentiator, integrator, subtractor, summing amplifier, then voltage to current converter, current to voltage converter, sample and hold circuit, then comparators, then square wave generator, triangular wave generator. Like that, so many circuits we can design, right? So many circuits we can design, and these are so many applications of OpAmp. So previous classes we have seen many, and in today's class sample and hold circuit, and after that comparators we are going to study, right? So let us see this sample and hold circuit. So the purpose of, before I start my class, I show one circuit. When I start my meeting, I just show one circuit so that people who join early, they can take this circuit. So all of you might have taken this circuit. Otherwise, while I am explaining, I am just showing only this circuit, but I am talking about several things. Therefore, meanwhile, you will be drawing this circuit. That is what I assume, and I talk. Okay, I explain. So let us see this sample and hold circuit. Sample and hold circuit, right? So here you just observe the input signal is given to this amplifier, right? So this is amplifier 1 and this is OpAmp 2, OpAmp 1 and OpAmp 2, and this OpAmp is connected in emitter follower configuration, right? Emitter follower means gain is equal to 1, here no RF, and okay. So now what happens? Emitter follower means whatever input voltage you give, same will be available at the output. No gain. Gain is equal to 1, emitter follower. Many times we have discussed. So even yesterday also we have discussed buffer amplifier, all that. So now your input, whatever you apply here, it is reaching this point. After reaching this point, it is allowed to pass through this MOSFET. So this MOSFET acts as a switch, right? This MOSFET acts as a switch. Now this switch is either closed switch or open switch, right? Switch may be closed between these 2 points. Switch is closed, or between these 2 points switch will be opened, right? So when the switch is closed, the circuit is short circuited and the signal passes through this. When the switch is open, now the input signal will not travel up to this point. Okay, so now this MOSFET acts as a switch, right? Now how this switch is closed and how this switch is opened means there is a control voltage applied to this gate of the MOSFET, right? So that means this gate voltage that you apply makes this MOSFET to be as closed switch or as open switch, right? So when you apply positive voltage, that means when the input waveform is at, let us assume that input waveform like this, right? 0 volts and 5 volts. When it is 5 volts, 0 to 5, then this switch will be, this MOSFET will act like a closed switch, and now it is like closed switch. Therefore, input that is reaching this point reaches through this and it reaches this point. And here there is a capacitor connected. So therefore, what happens means whatever input voltage that you are applying here, to that voltage this capacitor starts charging, right? So as long as the switch is in closed position, this capacitor will be receiving input signal. So therefore, capacitor will be charging to the input voltage like that, right? So it will be charging. Then the control voltage goes low, right? Control voltage goes low. When it falls from 5 to 0, then this switch will be like open. So no voltage is reaching the capacitor, right? So that time what should happen? The capacitor should start discharging, right? It should start discharge. But here the capacitor doesn't discharge because the emitter follower or the voltage follower or emitter follower circuit is here. So it has very high input impedance, right? So because the capacitor is like this, if there is, okay, it is receiving signal, now there is no signal. Now what it will do, now if there is any short circuit path, through that short circuit path capacitor discharges, right? But here there is no short circuit. Okay, what happened, it is almost like open circuit. There is one more op-amp connected here, and this op-amp has very high input impedance. Because of that, the capacitor doesn't have, here it is open and here also it is like open circuit. Therefore, the capacitor retains its charge, right? How long it retains its charge? As long as it is opened, it will be retaining its charge. Now, again the switch is closed. That means input control voltage is 5 volts now, right? So when the control voltage is 5 volts, the voltage across the capacitor will be same as that of input voltage. Therefore, what happens means the capacitor again starts receiving input voltage. So earlier the capacitor charged and that charge retains, and now input voltage is, you see, this is the input voltage. So during negative half cycle, we say the input voltage is going to negative half cycle. Therefore, the capacitor voltage will be just falling down, and by the time it reaches certain value, again goes control voltage goes up. Okay, so that means I will show you here, that will be better, right? This is the input voltage, this is the input voltage, this is the control voltage, right? Now let us see, right? Sorry, I'm not able to draw straight line. So now what happens? Positive voltage only, all that. Okay, now when VC is up to some voltage, the capacitor voltage is same as that of, that means capacitor voltage, let me show you one more thing. So whatever input is given here, that is connected to the non-inverting input terminal. Therefore, whatever voltage that is available here, because of the emitter follower, V0 will be same as Vin. V0 will be same as Vin. That means capacitor voltage is nothing but V0. Okay. So now let me show you this. This is the input voltage, and now control voltage is maximum. Therefore, that MOSFET acts as a closed switch. Therefore, capacitor receives this input voltage. Therefore, capacitor starts charging up to this. Now what happened? Control voltage has gone down to 0. Now the capacitor cannot discharge, right? This is the input waveform shown in dotted line, right? Input voltage is going down, but capacitor voltage remains same because across the capacitor there is what is that? Open circuit. Otherwise, at the capacitor we have emitter follower which is having high input impedance. Therefore, capacitor will not discharge and it will remain like that. Okay. So you observe input voltage is changing positive negative like that. So input voltage will be applied to the circuit like that. Here control is with the switch. Okay, therefore input voltage will be changing like that only. Now during this period, That means when the input voltage is in this falling time, this and control voltage is 0, therefore switch is 0, switch is open circuited. That time the output will remain at previous voltage only. Whatever voltage the capacitor is having earlier, the capacitor will remain at that voltage only. Is it clear to you? Right? Up to this, is it clear to you? Yes or no? Input voltage is varying like that, and during the time when the switch is on, the capacitor will be charging to that voltage, and when the switch is in off condition, actually capacitor should discharge, but across the capacitor there is infinite input impedance, amplifier is connected, therefore capacitor, though the switch is in open condition, capacitor will remain at maximum voltage only, right? So up to this, is it clear to you or not? Any one of you? Because if I say next one, you will understand, otherwise I'll repeat if it is required. Is this clear to you? See, input voltage is applied here, same input reaches this point, and here depending on the gate voltage or control voltage, the switch will be in on condition or in off condition. So if the switch is in on condition, the input voltage that is coming from here will reach this point, and capacitor charges to that input voltage, right? Up to that, is it clear? Are you connected in the class? Okay, let me ask in a different way, right? What is this arrangement, ma? What is this circuit? What is this circuit?
Emitter follower.
Very good, thank you. And what is this? This is also
Emitter follower.
same emitter follower, right? So now input voltage is applied because it is emitter follower. Input reaches this point, and what is this, ma? What is this?
Actual switch, ma'am.
Yes, MOSFET. Okay, MOSFET. You have studied about FETs now. Field effect transistor, N channel or what is that? P channel MOSFETs. You might have studied. Yes, FET as a switch. That's all. So just draw drain, source, and gate, and it is a FET. That is sufficient. Okay. Now this MOSFET acts as a switch. So when does the switch is open? When does this MOSFET switch is open?
Input is 0 volts.
Right. When it is closed?
Input is 5 volts, ma'am.
5 volts. Okay. Now, when the gate voltage is 5 volts, then the MOSFET acts like a switch, and this input that is available here is reaching this point. After reaching this point, what will happen?
Capacitor charges, ma'am.
Capacitor gets charged to input voltage, right? Input voltage. Then now the switch is in off condition. Then what will happen? Capacitor cannot discharge. Cannot discharge. Actually, it should discharge, but there is an open circuit here because high impedance circuit is there. Therefore, it cannot discharge. What it will do? It will maintain that voltage. That means it is holding that voltage. Previously, when control voltage was 5 volts, what is the voltage across the capacitor? That is holded. The capacitor is holding that voltage, right? So it is holding that voltage for some more time. So how long it is holding? Till next input it receives, right? When the control voltage goes high, again when it is 5 volts, then whatever input voltage is applied to that voltage, capacitor goes, and to that voltage capacitor, if it is low, it will go to that. Otherwise, if it is high, it will go to that. And now, as long as this control voltage is there, capacitor is filled with, capacitor is charged to input voltage. So input voltage is this. This is the input voltage. Therefore, during this time, the voltage across the capacitor is this much. Now, switch is closed, opened. Switch is opened. Therefore, capacitor maintains that voltage only. It doesn't discharge. Again, switch is closed. At this moment, what is the input voltage? This is the input voltage. So, capacitor receives this voltage. Like that capacitor, it is sampling the signal and it is holding for some time, sampling the signal and holding for some time, sampling the signal and holding for some time. Therefore, this on period of the control voltage is called sample signal, and off period of the control signal is called hold signal, right? Hold time period and a sample time period. Now you can change the hold and a sample time period. That means you can have control voltage at a very faster rate. That means you can take samples at a very high rate. Otherwise, you can take samples at a very low rate. Whatever manner you want, you can take samples, right? So the mainly the circuit function depends on this control voltage, how much sample you are taking, and how long you want to hold. This time period, the waveform width, everything you can change, right? That means the depending on the control voltage, the capacitor will be sampling and holding, sampling and holding the signal. Is this circuit clear to you? Is this circuit clear to you? Voltage follower, switch, and a control signal, and a capacitor. Right? Shall we move forward? Shall we move forward, or you want me to explain once again?
Once again, ma'am.
Once again. Okay, okay. Right? Sample and hold circuit. See, same person response I am listening. What about others? I think by the end of the class there will be some 50 or 54 students or 60 students, but I can hear only 1 or 2 voices, right? Please all of you try to respond. Okay. Now we are studying about sample and hold circuit, right? You see, this sample and hold circuit is designed with OpAmp, 2 OpAmps. Okay, 2 OpAmps are required. Here one voltage follower and another voltage follower. Then one switch is used here, and the operation of the switch is controlled by a control voltage. Okay, and for holding the signal we use a capacitor here. Right, now let us see how this circuit operates. This is the voltage follower, this is the voltage follower or emitter follower, right? Whatever input you give, same will be available at the output, right? And this is very familiar to us. Buffer amplifier or voltage follower or emitter follower, these are the alternative names, and we have studied about this exclusively in I think previous class or just before that. Okay, so we know about this. Whatever input you give, say we have proved that its gain is also unity. Now the input is reaching this point. Okay, now here MOSFET is connected. This MOSFET acts as a switch, right? This MOSFET acts as a switch, and switch is closed or switch can be opened. So closing and opening of the switch is controlled by a voltage called control voltage. So this control voltage is given to gate of the MOSFET. So if the voltage is high, the switch will be closed. If the voltage is low, that means 0 to 5. If the voltage is 0, switch will be opened. If the voltage is high, switch will be closed. So now we are explaining that with respect to waveform. Now switch is closed and opened, that's all. When the switch is closed, the input voltage that you have applied here is traveling through this switch and reaching this capacitor, and this capacitor will will charge to that input voltage. That means all the voltage that is traveling here will be reaching this capacitor, and this capacitor gets charged to that input voltage, right? So up to that it's okay. Whatever input you have, the same input will be available at the output. Therefore output will be like that. When the switch is closed, capacitor is charged to this voltage and output will be like that, because whatever voltage that is available across the capacitor will be same at the output terminal. Okay. Now the switch is opened because 5 volts comes to 0 volts. It is opened. Now it is like open circuit. So therefore no voltage is coming this side. Now what happens? The voltage that is across the capacitor will remain like that only. Will remain like that. Actually, if there is any short circuit or some other resistance, or if this circuit is having low resistance, then through that it should discharge. But this OpAmp has very high input impedance. Therefore, across the capacitor, it is like open circuit. Therefore, capacitor doesn't find any path to discharge. Therefore, it will hold that voltage. It will hold that voltage. Therefore, whatever voltage is available at the capacitor will remain at the output of the circuit. Therefore, output voltage will be like that only. Is it clear up to that? Yes?
Yes, ma'am.
Yes. Opened. When the switch is opened, so output is maintained at that same voltage only. Now the switch is closed. Next cycle. Next switch is closed means control voltage has gone to 5 volts. That time whatever input voltage is there will be reaching the capacitor. So whatever input voltage is there, to that voltage capacitor capacitor maintains that voltage. Therefore, when this switch is there, the capacitor will be having voltage that is available at the input. So that voltage is almost it is going down now. Therefore, that voltage is low. So it will be coming to the lower value. Same value will be available at the output. Now, how long it will be there? Next time the switch is off. So therefore, that low voltage it will maintain for some time as long as this switch is off. Again, the switch is in on condition. So whatever input voltage is there, to that voltage it will charge. So same thing we are showing here in the waveform. So this is the input voltage, positive, negative, like that. It is varying. Now the control voltage is varying like this. Now corresponding voltages we can observe, right? So this is what we have observed from the waveforms, right? So this is about sample and hold circuit. These sample and hold circuits are more and more useful in our communication systems and many other functions. Okay. Still, if you want further explanation, we will devote Monday and Tuesday hours for our revision. That time I will explain, right? Otherwise, if I go on, what is that, like tape recorder, if I go on, you have to pay little attention and listen. Like tape recorder, if I go on, repeat the same thing. So more than 10 times I have repeated this circuit operation, right? And I will be held up here itself and I cannot cover the next topics. Okay, so let me move forward. If you are not able to follow Monday and Tuesday, you keep all your doubts. You ask me your doubt, I will tell you clearly, right? Now let us see the comparator. Comparator means which compares two signals. And what are the two signals that can be compared with comparator? Let us see. There are two types of comparators, non-inverting comparator and inverting comparator, right? So why do we call it as non-inverting comparator? Means input is applied to the non-inverting input terminal, right? Then when we compare section A people with section C people. Okay. Similarly, that means when we say comparison, there should be minimum two components. So here the other signal, that is the reference signal, is applied at the inverting input terminal, and these two, if you observe, there is no feedback. Comparator is connected in open loop configuration, right? So if you see open loop configuration, gain is very high, 2 lakhs, more than 2 lakhs, right? So therefore very high gain. Therefore what happens means, if the output of the op-amp will be at either plus VSAT or at minus VSAT only. In between voltages will not be there, because it can withstand up to 13 volts only, 13 or 15 volts. But if the input voltage is more than that, we know that output voltage, we cannot measure what is that across the transistor 2 lakhs volts, you cannot measure. So transistor can give maximum value how much it can withstand. After that it will go to saturation, it will give plus VSAT and minus VSAT. Therefore here also the comparator will give its output either plus VSAT or minus VSAT, that's all, right? Because of the very high gain of the open loop configuration of the op-amp. Right, now this is the reference voltage, this is the input voltage. Now you just observe the waveform. This is the input waveform, right? Reference voltage is taken here, some positive reference voltage. Now as long as the input voltage is less than reference voltage, right? As long as the input voltage is less than reference voltage, output is at minus VSAT. Now if Vin is greater than reference voltage, this is Vin greater than reference voltage, right? So Vin is greater than reference voltage, then what happens? Output will be forced to plus VSAT, and again you just observe, this is the reference voltage. So from this period to this period, output will be at plus VSAT, right? And then when Vin is less than reference voltage, that means it is from here to here, Vin is less than reference voltage up to this. Therefore during this entire period, output will be at minus VSAT. Output will be at plus VSAT and minus VSAT only because of the high gain of the op-amp, and therefore, and again Vin is greater than V reference, therefore it will be at plus VSAT. So like that output will be changing from plus VSAT to minus VSAT, plus VSAT to minus VSAT. Like that, when the input voltage is greater than the reference voltage, output voltage is plus VSAT. Like that comparison can be done. So this reference voltage can be any value. So like that you can compare, you can design your comparator, right? So this is about reference voltage, some positive reference voltage, right? It is above 0 volts. Now here you take, this is 0 volts, reference voltage is minus some value, minus reference voltage, negative reference voltage. Now what will happen, right? As long as, same statement, as long as input voltage is less than reference voltage, right? So now you observe, this is the input voltage. Input voltage is greater than reference voltage. So Vin is greater than reference voltage. So output will be at plus VSAT. So Vin is greater than reference voltage. Vin is from 0 and reference voltage is some minus 1 volt or something. Therefore up to this, from here to here, output will be at plus VSAT, right? And as long as Vin is less than reference voltage, when Vin is less than reference voltage, output will be at minus VSAT. Output will be at minus VSAT. So like that, output will be changing from plus VSAT to minus VSAT, like that. And depending on the reference voltage that you take, you can design your comparator. So this comparator output waveform is with plus V reference, positive reference voltage, and this is with negative reference voltage. Is this clear to you or not? It is just difference amplifier, very high gain. So you will get V naught either at plus VSAT or at minus VSAT. Therefore, now this is what is that? Non-inverting amplifier. That's why same you are getting. That means plus V naught is plus VSAT or minus VSAT. Okay. So if Vin is equal to greater than if Vin is, when Vin is greater than V reference, that means this is Vin. When this Vin is greater than V reference, then output will remain at plus Vsat. Okay. If Vin is less than this reference voltage, output will be minus Vsat. Like that, the output will be changing from plus Vsat to minus Vsat only. In between values will not be there because of the very high gain of the amplifier. Right? This is about comparator. Right? Is this comparator clear to you? Is this comparator? We know the operation of OpAmp. Same OpAmp plus Vsat minus Vsat. That is because of the very high gain of the OpAmp. So this is why we call it as non-inverting comparator, ma? Why we call this as non-inverting comparator? Why do?
Because we are giving input at the non-inverting terminal.
Non-inverting terminal. Okay, then next case when we give input at the inverting terminal, then we say it as inverting comparator. That time what we do, just we exchange these two, right? So now here you observe this is the reference voltage. Here for convenience sake we are showing it as reference voltage. So another voltage source is required actually, but practically we don't connect another voltage source. What we do is we do like this, right? One potentiometer we connect, and this is supply voltage already which we are using. Between these two we will connect one one potentiometer. So we just slide this potentiometer pointer so that we can adjust this reference voltage. Any value of reference voltage you can adjust, and accordingly you can get the corresponding output. So this is a practical non-inverting comparator. Now let us see an inverting comparator, right? Inverting comparator, as your friend mentioned, input is given to the inverting input terminal. This is the inverting input terminal. Input is applied here. Input is applied here. And to the non-inverting input terminal, a reference voltage should be applied. So instead of connecting that reference voltage, we have connected this arrangement which I have mentioned. That is, between plus VCC and minus VCC, we connect a potentiometer. Depending on the position of this potentiometer, we will have the reference voltage. Whatever voltage you want, you can make that voltage as reference voltage. So a comparator, nothing is there in comparator. Just voltage V1 we give, V in or V1 voltage we give, and to the other terminal we give reference voltage. That's all. So if you just draw OpAmp, and of course these resistors, current limiting resistors we draw here, we include here. So what is that? Just input voltage at one terminal means, if you give input voltage at non-inverting terminal, you say it as non-inverting comparator. If you give input at inverting input terminal, you say it as inverting comparator. So comparator, again, if you draw these waveforms, input waveform and plus Vsat minus Vsat. But what you have to draw carefully is, when Vn is greater than V reference, it will be plus Vsat. If Vn is less than V reference, it will be at minus Vsat. So only that point you have to identify carefully while drawing this waveform, right? So this is what about inverting, non-inverting. Now let us see inverting amplifier, inverting comparator. So inverting comparator output will be minus of minus Vsat minus of plus Vsat. So just reverse to that we will get. That's all. Everything is same. So input waveform you just draw like this. Input waveform. Right. Let me take your attendance once so that we will not be in a hurry. Attendance. I think, have you observed any newness in our Teams app? I think today app interface is modified, I think. Right. Today I observe many changes in our app. I do not know whether you are using app or directly, I don't know how you are connecting. Are you all using Teams app in your phone? Okay. Right. Now let us see. This is the input waveform. input waveform, right? Reference voltage, some other reference voltage is mentioned here, right? When Vin is greater than V reference, when Vin is greater than V reference, it should be plus Vsat, but it is inverting amplifier. Therefore, minus Vsat we will get. So minus Vsat. So as long as Vin is greater than V reference, output is at minus Vsat. Once if you start minus Vsat, then plus Vsat, minus Vsat, like that. So this is the positive reference voltage, right? Instead of reference voltage is 0 here, reference voltage is positive. Now instead of positive reference voltage, if you write negative reference voltage, that means this one, positive 0 volts. Now this is negative reference voltage. When we take negative reference voltage, then what will happen? Same statement. As long as Vin is greater than V reference, output should be at plus Vsat, because it is non-inverting, it is inverting inverting comparator. Output will be minus of that, therefore it will be minus Vsat. So then plus Vsat, minus Vsat. You know there will be phase difference. Therefore, if you learn what is non-inverting comparator, and from that you can develop inverting comparator. So this is what about various comparators. Are these circuits clear to you or not? Comparator. I think voltage to current converter 7 marks question. Summing amplifier also 7 marks question you can expect. Then comparators also 7 marks question. Then sample and hold circuit also sometimes in this unit, sometimes in the next unit, somewhere once again we will get this sample and hold circuit. Again this can also be asked for, this will be asked for 7 marks, right? Comparator, if you are comfortable, okay, otherwise I will repeat. You tell me whether you are able to understand this comparator or not, right? Just comparator which compares two signals. Comparator, is it clear to you or shall I repeat? Shall I explain once again? Why output is at plus Vsat and minus Vsat we know. That is gain of the op-amp in open loop configuration is infinity. So we will not measure voltage across the transistor as a very high voltage. So transistor will be able to withstand some voltage only, and above that it will show saturation. Therefore, the output will be at plus Vsat and or at minus Vsat only because of the open loop configuration. Now, if the input voltage is greater than that, it will be at plus Vsat, less than that, minus Vsat. Okay. So, shall I move forward?
Yes, ma'am.
Yes. Okay. Practical non-inverting comparator, inverting comparator, then input and output waveforms. Have you taken these diagrams? You have to draw these diagrams carefully. See, non-inverting and inverting comparators. I think nothing is there. Just waveform plus Vsat, input waveform sinusoidal, output waveform plus Vsat minus Vsat. When do we have plus Vsat minus Vsat? You have to understand clearly. If it is inverting, how it will be. If it is non-inverting, how it will be. That's all. Right? So now the comparator with Zener diode at the output. That means this is just a comparator. These two signals are compared. One we call it as reference, other one is the input voltage. Anything can be V1 or V2. One can be reference voltage, other can be input voltage. So a comparison will be taking place. That okay. Now our aim is to mention why we use this Zener diode here, right? So these comparator, irrespective of the input voltages, right? If you want stable output, you know, Zener diode is a voltage regulator. If you give, for example, if it is a 5 volts Zener diode, it will give 5 volts only. But if it is, even if you apply 10 volts or 20 volts, whatever it may be, it will give same fixed voltage. So that means irrespective of the supply voltages that you use here, in order to get stable output, you can use Zener diodes at the output of the comparator, right? So that is what about comparator. Then the regenerative comparator. What is this regenerative comparator means? The third category of comparator, that is regenerative comparator. That means we have seen comparator circuit connected in open loop configuration only, right? So now regenerative means feedback. That feedback is also a positive feedback. How do you say that you are giving positive feedback or negative feedback? Output is connected to the inverting input terminal, we say that it is negative feedback. If output is connected at the non-inverting input terminal, we say it as positive feedback. Previously, we have used negative feedback and we have used OpAmp in for many amplifier applications, right? Now, this is a regenerative comparator. Regenerative comparator, that means output is fed back to the input to the non-inverting terminal. That means positive feedback is used here, right? So positive feedback, other name is regenerative feedback. Positive feedback, other name is regenerative feedback. For the other one, negative feedback, degenerative feedback we say, right? So with positive feedback, again, we will achieve very high gain, very high gain. And you know, when we say regenerative or positive feedback, we say that loop gain, and it will act as an oscillator also, right? So this is the circuit diagram of a inverting, what is that? Regenerative comparator. The other name to this is a Smith trigger, right? So let us say regenerative comparator or Smith trigger, right? Just you are giving input voltage here, input signal here to the inverting input terminal, and you are giving some feedback from output to the input to the non-inverting terminal. So positive feedback you are applying. Positive feedback you are applying. So depending on the volt, that means of course there is some reference voltage here. There is some reference voltage. So if the reference voltage changes, then the output changes. That means of course we say that the output voltage is forced to, the output voltage is forced to move between plus Vsat and minus Vsat, right? Why? The output voltage, any comparator, because of the high gain. Now this positive feedback also provides very high gain, and this high gain makes this comparator to move, to trigger or to switch between plus Vsat and minus Vsat, right? Then how it triggers between plus Vsat and minus Vsat means, if the input voltage Vi, it triggers between the output voltage V0, right? One second, I will show you this. This is better, right? This is the input voltage. This is the input voltage, and this is the output voltage, right? How the output voltage changes because of the positive feedback? It is clear that output changes between plus Vsat and minus Vsat. Then when it goes to plus Vsat and when it goes to minus Vsat, we have to understand. Okay, so previous circuit, we know output is fed back to the input, so this will act as a reference voltage. Okay, so whenever there is whenever input triggers the output to plus Vsat or triggers output to minus Vsat, depending on this reference voltage, So this is about Smith trigger, right? The output, these trigger voltages, right? One trigger voltage is called what is that, upper threshold point, and another voltage is called lower threshold point. Okay, that means Vsat, V0 will be at plus Vsat, and when the upper threshold point occurs, it goes to minus Vsat, and it will be at minus Vsat. Again, when it changes its minus Vsat to plus Vsat, when it reaches lower threshold point, right? So what are these upper threshold and lower threshold points? Means this is the voltage, right? So when this voltage, depending on this voltage, the output will be triggered, right? Output will be triggered to the output will be triggered to change between plus Vsat to minus Vsat. Okay, so the input voltage Vi triggers the output voltage V0, right? So the input voltage Vi triggers the output voltage V0 every time when it exceeds certain voltage levels. So what are these certain voltage levels? When it exceeds lower threshold potential, and these voltage levels, these are called upper threshold and lower threshold potentials. Okay, so this is what about Smith trigger, and with this Smith trigger I would like to stop here, and in the next class we shall discuss about square wave generator and triangular wave generator, right? Square wave generator, two types, stable multi and monostable multi. So you have studied without OpAmp. Now stable multi and monostable multi with OpAmp we are going to study. After that, when we know square wave, when it is given to what is that, integrator or differentiator, we will get a triangular wave. That's all, right? So with that we will be able to complete our unit 3, and those things we will discuss tomorrow. If at all, if I miss any of the points, we will discuss in our revision class, right? So this is what for today, and let me take your attendance once again, and I'll stop today's class. Okay, this interface is changed now, so okay, download attendance. I have downloaded. Then I will stop here, stop recording, and this record will be available